All right, so this first section is going to talk about bonding and electronegativity. Ionic bonds are formed between ions and ionic compounds. They're the result of electrostatic interactions that are going to occur between these oppositely charged ions. One or more valence electrons is transferred from a metal atom, turning it into a positive cation, to a nonmetal atom, turning it into a negative anion, or this takes place with polyatomics. And these bonds, because there is that physical transfer, are always going to be considered as polar. And you can see down there in the picture, you have the electron transfer from the element that's being oxidized, your reducing agent sodium, to what's being reduced, which would be the chlorine ion, which is acting as your oxidizing agent. And when they do this, they now have a complete valence shell. They have the configuration comparable to a noble gas. Coulomb's law is one way we can assess the amount of energy that is stored in this bond. It is the lattice energy is the energy that would be required to break that bond once it has formed. Or it would be, if you're going to look at it in another direction, the amount of energy that is released when those atoms come together to form ions. So there's that constant there. I'm never going to ask you to solve for E with Coulomb's law, but basically Coulomb's law allows us to assess, when we're comparing compounds, which one is going to have that stronger ionic bond. The stronger ionic bond would be associated with Coulomb's law directly. If you have a greater charge product, that's what Q1 and Q2 are, the charges of your cations and anions, and you have a smaller radius, you are going to have a greater amount of lattice energy. Covalent bonds are going to be those that form between electrons that are physically shared between atoms. Sometimes you will have atoms that share electrons equally. That would be a nonpolar covalent bond, which is what we're seeing with these two chlorine atoms. There's no, they have similar, they have the same, identical electronic structure in terms of protons, in terms of shielding, so there's no reason for them to share electrons differently. However, if bromine was paired with chlorine, or if bromine was paired with iodine, you would be more likely to have a polar covalent bond, because those atoms are going to have different amounts of shielding, they're going to have different nuclear charges, and so when it comes to elements within a group, the shielding is going to dominate. When it comes to elements across a period, it's your nuclear charge. Electronegativity is one way to assess this. Basically, it's the ability of an atom present in a molecule to attract a pair of electrons to itself. The bigger the difference is in electronegativity values between elements in a bond, the greater that ionic component is, the more polar your bond will be. You will notice here in this electronegativity chart, I do not expect you to memorize these values, but you should be able to understand the trends that are being represented. You will notice that the electronegativities increase going across a period. Fluorine is your most electronegative element. It's one of your smallest atoms, so its valence electrons are going to be strongly attracted to its protons, its nuclear charge. So the nucleus is going to be more involved in any sort of interaction it's going to form. Where if you look down on the bottom left-hand corner, you'll see that like cesium and rubidium and barium, they have very small electronegativities. As shielding starts to dominate, as the nucleus gets less attracted to the valence electrons because it's further separated from them, the desire to gain a pair of electrons is going to diminish. So with these three compounds here, it says which ionic compound in the following sets has the greatest lattice energy according to Coulomb's law? What evidence do you have that supports this? Well, Kf and Kbr are both ionic compounds. Potassium's +1 as an ion. Fluorine and bromine are both -1s. So the charges aren't going to have a significant impact on the amount of lattice energy. The size of our ions, however, will. And fluorine having fewer filled valence shells, has less separation between the nucleus and its valence electron, which means it's going to be smaller. So Kf would be the ionic compound of this pair that has the greatest lattice energy due to that smaller radius. Remember that the lattice energy is proportional to the charge product of your cation and anion divided by their radii. In our next example, we have MgCl2 or AlCl3. We definitely have a different charge product. Magnesium is +2, aluminum is +3. And if we look at those two elements, I believe aluminum is even just a little bit smaller than magnesium. So AlCl3 has the greater charge product. 3 times -1 would give me -3. 2 times -1 would give me -2. And it's just a little smaller. So I don't know if size would have had that much of an impact given that they're right next to one another on the table, but the charge product definitely is going to push it towards aluminum chloride. Finally, with letter C, we have barium iodide and aluminum phosphide. Barium's +2, iodine's -1, so its charge product is -2. Aluminum's +3, phosphorus is -3, so its charge product is -9, substantially larger. And if we look at the location of aluminum to barium and phosphorus to iodine, I believe you're going to see that barium and iodine are larger. They have more shielding compared to aluminum and phosphorus. So, sorry, I forgot to put the explanation there for B. So aluminum phosphide is going to be the compound with the greatest lattice energy of this pairing because it had both the charged product and a smaller radius. So now I'm going to ask you to rank these elements based on increase in electronegativity. Sodium, potassium, rubidium are in the same group. As you go down a group, electronegativity diminishes. So rubidium would have the smallest, sodium would have the biggest, potassium would fall between them. In our next set of choices, sulfur, oxygen, and fluorine. The one that's closest to fluorine is going to be your most electronegative, so fluorine. The one that's furthest away is going to be your least electronegative, that would be sulfur. It has a little bit more shielding than oxygen, so its electronegativity diminishes. Finally, in this section, you were asked to predict which of the following bonds would be the more polar, BF or BCl. So without that chart, you would have to take a look at the location of these elements on the periodic table. Fluorine and chlorine are in the same group, but I believe there is a greater difference in location between boron and fluorine than boron and chlorine. We know that fluorine is more electronegative than chlorine because fluorine is higher up in the group. So if boron's electronegativity value is not going to change, the difference would be a little bit greater with fluorine than it would be with chlorine. Your negative pole would be the element that's the more electronegative one, which would be fluorine. So boron is the most positive. A couple other ways you can write this. You could draw an arrow showing the arrow pointing towards fluorine, that fluorine is your more electronegative atom. Or you can do the partial positive or partial negative.